So in this video, I'm going to complete the example that we started in class. And what are we supposed to do here? Well, we're supposed to find the volume of a pyramid with square base with side lengths A and height H. Okay, well, as in class, I've drawn my pyramid here so that the center of the base of my pyramid lies at the origin, where I've drawn this set of axes, y-axis and an x-axis. Now, what do we know? We know that this pyramid is supposed to have a square base of side length A, and it's supposed to have height h. Okay, so that means on the y-axis, this point here is h, and if the side length here is supposed to be a, then the distance from here to here is a, and that makes this point here on the x-axis a by 2. So just write that on. So this is the point a over 2. Okay, well, as noted in class, what are we going to do? Well, we're going to try to find this volume by slices, and it's most natural in this case for us to consider horizontal slices. So we'll take horizontal slices at y. So they're going to look like this, I guess. Like so. Okay, so this would be a slice taken here at y. Okay, so what do we need to do? Well, we need to find the area of this slice so that we can then thicken it up, multiply by a dy to give us a volume of a square slab at y, and then we'll add up all those volumes of the square slabs, one for each y. In other words, we'll integrate from 0 to h. Okay, so let's see. Let's write this down then. Let's let a of y equal the area of the slice at y. And the reason that it makes sense for us to use these horizontal slices at y is because we're going to have to find a formula for a of y, and because our pyramid has a square base, each of these slices, this has a square base here, so each of these slices at y, these horizontal slices at y, are also going to be square. It should be clear that the distance from here to here is going to be the same as the distance from here to here. I could just move my axes around. It's perfectly symmetric here. So if this distance is this distance, well, then this distance is this distance here. In other words, this side length is the same as this side length here. So this is going to be a square. So let me just write that. So this is a square. Okay, so now we're going to need to find a formula for a of y. But let me first maybe just say why are we doing this. Well, if we have this, then what can we say? The volume of S, as always, what do we do? Well, we will sort of thicken our slice up a bit by width dy, and the volume of our slice at y is going to be a of y dy, and we'll add these up, and we'll have one slice for each value of y between 0 and h up here, so we'll integrate from 0 to h of a of y dy. Okay, well, now what? So now we need to find, as we said, the formula for a of y, which is going to be a square. So how are we going to do that? Well, let me just move over here a bit, and I'll draw a picture of our slice at y. So here's our slice at y. Make it blue. So here is our slice at y. And I'll draw it head on in 2 dimensions like this. As we said, it's going to be a square. And we need to know, in order to find its area, we need to know its side length. If we know the side length here, we know that the area is going to be this number squared. Well, what we'll do is we'll try to find this value here. So if we can find half the side length, x, as shown here, I'm going to draw it onto my slice in my pyramid over to the left. Hope you can see that. Then this is going to be 2x. All right. So how are we going to find this distance x here? Well, looking at the pyramid, again, on the left, looking at the pyramid here on the left, we're looking for our value of x here. And what I'm going to do is I'm going to take a peek at this triangle here that we would get by intersecting our xy plane, positive xy plane, I guess, the first quadrant of the xy plane, with our pyramid. So we'd end up with a triangle like this. Let me draw that on. So I'll draw it in red. So, like so. And we have this triangle right here. So let me draw the triangle over on the right-hand side. So this is that same triangle. It seems to have gotten a little bigger. That's okay. And what do we have? Well, we notice that what we're looking for here is this value of x. So that's what we're looking for. Now, we know that our pyramid has height h, so the height of this triangle is also x. And we also know, looking over again at our triangle here, that this length here is a over 2. So we'll write that on. And we also know that this length up here is y, because our x happens at y. Okay, so write that on as well. So this, as we said, is a over 2. And this distance here is y. And we need to somehow find out what x is from this. And in fact, how we can do that is we can use similar triangles. In fact, if this length up that we just wrote down was y, then this vertical length here on our smaller triangle is h minus y. All right, so here's what we have here. So this length right here is h minus y. Okay, so looking at this, what are we trying to do? We're trying to solve for x somehow, right? We're trying to solve for this length here, x, in terms of y. And how can we do that? Well, what you notice is that we have 2 similar triangles. They share exactly the same angles, so they are similar. One fits perfectly inside of the other. And what we know about similar triangles is that ratios of corresponding sides are equal. So, by similar triangles, what can we say? Similar triangles what can we say? Well, the ratio of the vertical side on the small triangle, actually let's do this the other way, the ratio of the horizontal side on our small triangle, which is x, is to the vertical side on our small triangle, and that ratio is going to be the same as the length of the horizontal side on our large triangle, which is a over 2, by the vertical side on our large triangle, which is h. All right, so x is to h minus y, that's what we wrote here, as a over 2 is to h. That's what we wrote here. Okay, so now we can solve for this x here. Remember, we're looking for this value of x. There it is. We can solve for it. What can we say? X then is equal to a over 2 times h minus y all over h. Okay, so we now have x as a function. So we now have x as a function of y. Let's put that over here. So now we know that 2x, the side length of our rectangle, is going to be twice this value here. 2 over 2, that's going to cancel. So this 2x is going to be equal to a times h minus y over h. So let's just write that in. So we now know that this length here is equal to, I guess I'll write it as a over h times h minus y. All right? Okay, so we now have the side length of our square slice at y. That means that we can determine the formula for a of y. A of y is equal to the side length squared. So it's going to be a squared over h squared times h minus y all squared. So what's that? This is equal to, this is equal to, multiplying this out, a squared over h squared times h squared minus 2hy plus y squared. All right, so now we have what a of y is. Now we can compute our volume, because remember, our volume of our pyramid was equal to the integral from 0 to h of a of y dy. That's what we said before, and in fact, if we travel around over here, that's what we said. So a of y dy being equal to the volume of our infinitely thin slice at y. We add one of these volumes up for each y between 0 and h. In other words, we integrate from 0 to h. All right, so let's go back and we'll now compute the volume. All right, so the volume is equal to the integral from 0 to h, as we have up above, a of y is equal to a squared over h squared times h squared minus 2hy plus y squared, let's ignore that, dy. Right? So what's this equal to? Well, remember, the a here and the h, these are constants, right? So this was the length of our square base, and this was the height of our rectangle. These are constants. Y is the only thing that we're integrating with respect to, so we treat these all like constants. So what do we have when we take our antiderivative? Well, we get a squared over h squared. Then we have h squared y minus h y squared plus 1/3 y cubed, and this from 0 to h. Right? This is equal to a squared over h squared. So, letting y equal h first, we have h squared times h, that's h cubed, minus h times h squared, that's also h cubed, plus 1/3 h cubed, all right, minus, what do we get when we let y equal 0? Well, we get 0 in each of the terms, so we just get 0. So this is a squared over h squared. The h cubed minus h cubed is 0, and we have just 1/3 h cubed. And canceling those h's, we have 1/3 a squared times h. Okay, so what's the volume of a pyramid? So what's the volume of a pyramid with square base and height h? It's 1/3 a squared times h. I'm just going to go back. What am I doing? This is what I'm doing. I'm going to come back over here, and I'm just going to write this down. What did we find? We found that this volume is 1/3 a squared times h. All right, so the volume, as we said, of a pyramid with square base, side length a, and height h is equal to 1/3 a squared times h. That's 1/3 times the area of the base times the height. Interesting. And now, as an exercise, why don't you try this? So, what are you supposed to do? Try to find the volume of the cone. And what's a cone? Well, a cone is a pyramid with a circular base. We just dealt with a pyramid with a square base. You will be dealing with a pyramid with a circular base. So find the volume of the cone with base radius r and height h. And what you should discover is that the volume is equal to 1/3 times the area of the base again, pi r squared, times the height. So sort of interesting. In fact, this would be a formula that you were probably given when solving max-min problems in Intro Calculus 1. And now you see that you can actually derive the formula for the volume of a cone with base radius r and height h using our techniques. So, pretty amazing. Enjoy.